In this video, we're going to cover section 1.9, reversible reactions and equilibrium. So in the kinetic models discussed previously, we assumed that once reactants formed products, that the opposite or back reaction didn't occur. However, reversible reactions are definitely possible. So let's consider the following reaction, in which the forward reaction, A to B, is first order in A, and the back reaction, B giving us A, is first order in B. The rate constants for these two paths, the forward rate constant we'll call K1, and the back rate constant we'll call K minus 1. Integrated rate law expressions can be obtained for this reaction, starting with the differential rate expressions for the reactant and product. So as we've seen previously, if we take the time derivative for A, dA dt, it's equal to two terms. The first term minus K1 times the concentration of A representing the forward reaction, and plus K minus 1 times the concentration of B representing the reverse reaction. Similarly, we can look at the differential rate expression for B, and the two terms are identical except for the sign. So they just represent opposite directions with respect to the formation of B compared to that of A. Now, similar to the initial conditions used in previous examples, if only the reactant A is present at T equals 0, then the sum of the reactant and product concentrations at any time must be equal to that initial concentration of A. So we set this particular initial condition. In doing so, that allows us to substitute for the concentration of B in the following expression. So if we're solving for dA dt, we have two terms, one with respect to the concentration of A, the other with respect to the concentration of B. Using this initial condition, we can solve for B, which is equal to the initial concentration of A minus the concentration of A at some time t. So we make that substitution in this step, and then we can multiply through and collect like terms, and we end up with the following expression, where we have a minus bracket K1 plus K minus 1 times the concentration of A plus K minus 1 times the initial concentration of A. So this is your constant. So this becomes the form of the integral that we must solve to get solutions for both the concentration of A and B. So again, here's our integral. It's equivalent to the standard integral shown here, the integral of dx over A plus bx. So again, A representing this constant, B representing the sum of the two rate constants K1 and K minus 1, and x being the concentration of A. And integration results in the following expressions for A and B. We see that A is equal to a quotient which has two terms in the numerator, one being an exponential term, and the denominator is the sum of the rate constants, all multiplied by the initial concentration of A. Similarly, we have for the concentration of B, in brackets, 1 minus a very similar term, again with this exponential dependence, all multiplied by the initial concentration of A. Now we can note, as we just stated, that the concentration of A undergoes an exponential decay, but the decay is with respect to the sum of K1 and K minus 1. So we call this the apparent rate constant, or we've used the terms effective rate constant previously. Similarly, B grows in exponentially with the same sum of those two rate constants. So shown in this figure is a graphical representation of a reversible reaction involving two reactants, A and B. And you can see that we have an exponential decay of A, and at the same time we have an exponential growth of B. It's important to note that if the back reaction were not present, that we would expect A to decay exponentially until it reached some concentration close to 0. However, because there is a back reaction, what we observe is that both the concentration of A and the concentration of B reach some non-zero value at long times. Now, the concentration of reactant and product at long times, this is defined as the equilibrium concentration. The equilibrium concentrations are equal to the limit of the previous expressions as time goes to infinity. So if we go back to those expressions, as t goes to infinity, e to the minus, as the number approaches infinity, is going to be a very, very small value. And so in fact, this term will approach 0 as t goes to infinity. So that simplifies the expressions for the concentration of A and B as we approach those long times. So you can see the result is that we're left with the concentration of A now with the subscript EQ to represent the equilibrium concentration. It is equal to a quotient of the rate constants, k minus 1 over the sum of k1 plus k minus 1, all multiplied by the initial concentration of A, whereas B at equilibrium is equal to 1 minus the same quotient times the concentration of A initially. So as a result, the reactant and product concentrations reach a constant or equilibrium value that depends on the relative magnitude of the forward and back reaction rate constants. Now, after equilibrium has been established, the time independence of the reactant and product concentrations, we can express that in this way, where the change in the concentration of A at equilibrium with time is equal to the change in the concentration of B at equilibrium over time. And we can set these two differential rate expressions to 0. Now the subscripts EQ, they indicate that equality applies only after equilibrium has been established. A common misconception is that this expression states that at equilibrium, the forward and back reaction rates are 0. That's not true. Instead, at equilibrium, the forward and back reaction rates are equal, but not 0, such that the macroscopic concentration of reactant and product does not change with time. That is, the forward and back reactions still occur, but they occur with equal rates at equilibrium. Now, using this expression in combination with the differential rate expressions for the reactant, we arrive at the equilibrium constant, defined in terms of concentration and related to the ratio of forward and back rate constants for the reaction. So again, we can equate the change in the concentration of A at equilibrium with time equal to 0 when we establish this equilibrium condition, and we can equate that to the differential rate expressions for the reactant. Note that we're now including the subscript EQ. So if this part of our expression can be equated to 0, then we can rearrange it such that we're solving for the equilibrium constant. And so this equilibrium constant can be expressed in one of two ways. It can be expressed in terms of the concentrations of B and A at equilibrium, or it can be expressed in terms of a ratio of the rate constants, K1 over K minus 1. Overall, this understanding provides a practical method for determining the forward and back rate constants. Specifically, measurement of the reactant decay kinetics or the product formation kinetics provides a measure of the apparent rate constant, K1 plus K minus 1. And we'll see in an upcoming video, we'll be looking at perturbation relaxation methods that allow us to determine just that. Also, the measurement of the equilibrium constant or the reactant and product concentrations at equilibrium, this provides a measure of the ratio of the forward and back rate constants. And there are a variety of methods we can use to determine an equilibrium constant. We can use quench methods, we can use steady state, non-time resolved methods such as absorption and fluorescence spectroscopy to determine what K is for a reacting system at equilibrium. Together, these measurements represent a system of two equations and two unknowns. And so as a result, we can readily solve and determine what K1 and K minus 1 are. So if you have any questions about reversible reactions and or equilibrium, by all means, send me an email. Thank you.